Welcome to another video on the F769 Discovery Kit. In this video I will finally get to write some code and do something interesting. The previous videos have been a preparation to this point. I'm going to do some simple board bring up of the LEDs and UARTs. During this process I will be flashing the target multiple times. So the first thing I'm going to do is improve the build system so it is more convenient to flash the target as often as I please. Okay, so I want to turn the LEDs on. I'm here in the main.c. Now because this is a free RTOS application, I want to insert my code just before control is passed to the scheduler. This is the safest place to insert my code since at this point I don't know what any of the above stuff does, and I'm assuming it's full of landmines and traps. Let's call it app bsp bring up. We can define it up here. Let's make it static. Alright, so I want to initialize and turn on or off the LEDs. So where will that be? So we have these. I'll look at the headers because that's the interface that should tell you what you can do. So none of these say LED, so I'm going to assume that it's in this one. Okay, we got our labels for the red and green. Okay, scanning through here. Okay, got some USB stuff, push button, SD, touchscreen, LCD, lots of stuff. Okay, here's the actual interface. Okay, I like to see this. This clearly explains what's going on, so hopefully I can assume that this does what it says. Okay, I'm gonna init both of them and let's turn them both off. As you see there's a few LEDs on. Just by looking at it in the picture, I don't know which one's which, so let's turn them both off. So we gotta give it the LED type, def, enum here. So we got a red and a green. So let's init the red, init the green, turn them both off. Alright, let's see what that does. Can build. Okay, built. Now over here I'm out of the container and in the host, so I can communicate with the flashing laptop. Remember that the laptop I'm developing on is not the same as the one connected to the Discovery Kit. So also in a previous video I created this script here, flash target remote, which copies the ELF file to this remote host and then runs a shell script on the remote host. So this was a hard-coded name which no longer is applicable. This is not the name of the ELF that was just built. So this is the improving the build system part. What I want to do is change the name of this. Now obviously I don't want to change the name of this every time, so two options would be I could make this a parameter and supply the name as a parameter to this script, or what I'm going to do is I'm just going to say copy latest.elf. So whatever latest elf is the one that will be copied over to the remote host. Now at this point there is no latest elf. The way to do that is I'm going to do that in CMake lists. CMake lists. Now at the bottom of the CMake list here, I'm going to copy in some stuff. Now what this does is it adds two custom commands here. The second one is the important one. It is a post build command. So after the build is done, it's going to run this command. Copy the output elf name into latest.elf. So wherever the elf ends up will get copied into a file called latest.elf. Now here's just a little convenience thing that I like. It adds some info to the file name, in this case the name of the branch and the shortened commit SHA. It's a little bit arcane here, but that's what it does. So it'll say master and then the commit SHA. It stores the result of this echo command into the variable get repo info. Okay, this was copied over from the other project, so I'm gonna change it up here. Target base name. I'm not going to include any build versioning info, like a major and a minor number. I want to change this to base name here, just so it's more accurately saying what's happening. Set target properties, the first parameter is the name of the target, and that the name of the target is this variable target base name. The output name is, this is the name of the elf. Now add custom command to the target, this target. Right, so size is what you're used to, which is at the end of the build it tells you how big all the sections are. Output exe base name. Just to show that again. Okay, we have latest elf and this more verbose name. So now I can go here to the host and run that flash target remote script. Now, as we noticed before, this takes forever. It takes so long that you don't want to do this very often and wait for it. Now, the longest section that gets loaded is the external flash. So the next thing I'm going to do is not load the external flash. One, because I don't care about it, but two, I believe it should only have to be loaded once, as it is non-volatile memory, probably full of static data. Oh yeah, also point out here we have the output of the size command. It tells us how big all of our sections are. It's good to mentally just keep a side note of how big the sections are so you can notice sudden unexpected changes. Okay, you saw there, the target just reset. Yeah, this XQSPI flash section is the biggest one, so we want to just not load that. And the way that you do that is in the linker script. Alright, let's open up the linker script .ld. So the linker script is, it tells the linker how to link together the elf, and the elf is what tells GDB what to load onto the target. We have the memory map here. It's saying the SPI flash it starts at address 9000, 16 megs long. Here we have sections, like the ISR vectors, text section, data, etc. And here it's saying that QSPI flash section will be loaded at the start of the QSPI address 9000. So taking the lead from these sections, which I have no idea what they do at this point, but I do know that if I say no load, then it won't load. And then it can build. Didn't say linking. I'm just going to make a trivial edit to main.c just in case, just to force the linker to go. Remove some of this stupid white space. Alright, it relinks. I can do that again. Notice how convenient it is to just flash. Now it still takes a long time, not nearly as long, so yeah. We see here, external flash section was not loaded. It still takes about 10 seconds at 86 kilobytes per second. I think this can be sped up by configuring OpenOCD to run faster. But yeah, still these sections are still big, text and RO data. So this 80,000 hex is 500 kilobytes. Still pretty big. We'll just live with it for now. Yes, so notice here the LEDs on the right of the picture, to our right, are off. Before, there was one of them that was on. And sorry about the blurriness, I will get a better camera. So upon visual inspection of the board, this is the power, and next to it is VBus. The reason that they are red and green and right next to the red and green user LEDs is completely baffling to me. It's almost as they chose the worst possible place to put them. So anyway, I'm going to take a few layers of electrical tape and block those out. So now I can really be sure the behavior is as expected by, let's turn on the green one. Make and flash. if I wasn't running in the container, what I would do is make 2 ampersands and then the flash target remote. This says that if the make is successful, then flash, so it could do it all in a one-liner. But the Docker container does not have access to the remote laptop, so can't do that. And here we see very blurry that the green LED turns on next to the electrical tape. Okay, now I'm going to get the UARTs working. So the 769 Discovery Kit has headers available for 2 of the UARTs. Now I'm going to look through some documentation to figure out what pins they are, and then I'm going to look through the CubeF7 firmware package to find some projects that drive the UARTs. Alright, I'm going to find the pinouts first. Down here in the appendix, I/O assignment. So we have, these are the pin names of the microcontroller, and over here is more of the external name. So let's look for UART stuff. Okay, UART 5 RX, write that down. UART 5 RX is PD2 and Wi-Fi TX. TX, UART 5 TX, PC12 Wi-Fi RX. VCP TX, that down. USART 1 TX, PA9 VCP TX, UART 6 RX, PC7 RD0. That'll be the Arduino header. D0 in Arduino terms. USART 6 TX. What is USART 1 RX? USART 1 RX, PA10 VCP RX. Okay, so I have the UART instance numbers 5, 1, and 6, and I have their microcontroller pins. Now let's find where they are on the Discovery Kit. Wi-Fi TX, so want to look for some kind of, header, something external here. So we have Wi-Fi TX is header pin 8, Wi-Fi RX is header P1. Okay, now where is VCP TX? Okay, don't want it on this page. Okay, what is this? The trick I like to do is zoom in a lot, so the search result is more clear. A lot of times it's really difficult to see where the search match was. Okay, VCP TX. Okay, this is the ST-Link chip. This is the serial port for communicating via the ST-Link, so I'm not going to use that. So USART 1 will not be used. So we have 5 and 6. Can never double check this too many times. Okay, here's the, you can tell from how it looks, this should be familiar as the Arduino header shape with the classic not aligned 2 headers here. Okay, yeah, this is as expected. D0 is the first pin here. Lastly, I want to point out Wi-Fi TX. So this header here, when I go to look for it, I'm not sure that pin 1 will be identifiable, so worst case, I can identify pin 1 by looking at VCC and ground. VCC is pin 2, ground is pin 7. And that's all I need from this document. You see the header there in the corner, and there's some space cleared out there for the external daughter board to go there. I think it's implied that that extra space is where you see this PCB antenna there. So if that is the case, then that does identify the polarity, but of course you can't trust these vendors, so I'm still going to go ahead and use my meter to test for VCC and ground. Okay, bottom left to top right. And I know you can't see this. This is my cue to get a new webcam. Okay, got 3.3, as expected. Okay, so I've hooked up my scope here, So now I can start playing with some code. I'm using the scope to test the transmitter because then I can check the timing of the transmitted bytes and I don't have to worry about whether the receiver is working correctly. So again, you can never double check this too many times. So it says RX here, but actually that is UART TX. So UART 5 TX is Wi-Fi RX. Wi-Fi RX is the header pin 1. This being the header pin 1 is the UART TX. And again, I know you can't see it, you'll just have to trust me, the scope is connected there. And here's just a little tip. These audio jacks there, you can generally assume that they're grounded. So now, of course, don't take my word on that. You should always check with the meter, especially if your scope is grounded, meaning if it connects to the wall. Lots of scopes today are battery powered or isolated, in other words, so it is all too easy to forget that you can accidentally short something to ground via the ground clip. Okay, now that the scope is connected, I can start writing some code. First, I want to find some project I can use as a reference. So here I am at the top of the STM Cube firmware. Let's go into projects. So since I'm looking at the UART stuff now, and that's a board level thing, or I'm sorry, it's not a board level thing, but a microcontroller level thing. In other words, the interface to the UART is the microcontroller pins themselves. So technically I could use either of the 769 boards, but anyway, I'll just start with the Discovery. So let's find anything that says UART or USART. Okay, we got a UART 2 boards COM DMA. Let's start there. So navigating to that project here, start in main. Okay, so what does this do? Yeah, this really doesn't do much, so that's good. Simple is better. So here we see that inside of main, the UART is initialized inline, so nothing hidden from us. That's good, as the whole point of this project is to be a UART example. So looking here at the UART init, it's actually quite simple at the UART level. The confusing part is the fact that there's actually 2 levels you have to configure. I've never seen this outside of ST, so it may be specific to ST. If anybody has seen it somewhere else, please mention. Anyway, there's the UART level, which is what's highlighted here. This is the higher level. And then there's the MSP, which is the lower level. MSP for microcontroller support package, so think BSP but MSP. What's shown here is the high level, which talks about baud rate, stop bits, parity, etc. High level as in describing the properties of the communication link. How will the 2 devices communicate? So that's nice and clear. This is actually all you have to do before calling init here. And then you're thinking, well, where's all the other stuff that has to be initialized? I've used ARM processors and other processors before, and there's no way I can just say initialize UART 6 and it just works. There has to be more configuration. You would be correct in thinking that, and actually what happens is inside of the UART init, it makes a call to HAL UART MSP init. So here's inside of the HAL driver layer. It's going to call this here HAL UART MSP init. Okay, so where is HAL UART MSP init? Oh, what do you know? It's buried further into this long file. And what do you know? It's a weak symbol. And if you don't define it yourself, it gets defined to nothing, and it will conveniently not tell you anything. It will conveniently not tell you that you have to do this, and if you don't do this, there's a 0% chance of your peripheral working. So following the open-close principle, you don't want to insert your code here. Really, you don't want to modify any of this code at all. So this project has the right idea and has a file here called HAL MSP. Okay, inside of HAL MSP. So here we have the tricky part. This is the part that you're liable to get wrong, especially if you are doing it from scratch. That's why it's good to have a reference. Start with a working reference and modify it to your needs. So the MSP does stuff like enable peripheral clocks, configure GPIOs, configure DMA, and interrupts. Here I don't want to use DMA, so I can just delete all the DMA stuff and that'll be fine. Once you understand this two-layer architecture, it actually does make sense. It's just very confusing the first time seeing it. I didn't know this existed when I first saw it, obviously. Discovering this was buried inside of the HAL layer inside of ifdefs, so it was quite confusing. And this file here, it only has one function, init, besides the dinit, but I won't be de-initting anything, so yeah. So one problem with this architecture is it doesn't have any regard for if you want to use two UARTs. To explain, so here when you call HAL UART init, it says, okay, I want UART 6 to have these properties, this baud rate, stop bits, but regardless of what parameter you give the init function, this handle, this init function will always call the same MSP init function. So it is implied that inside of this one function, HAL UART MSP init, you will do the initialization for all of the UARTs, not just one. In my case, I'm using UART 5 and 6, but the way that this HAL layer is written is suggested that I initialize them both in this one function. That doesn't really make sense because when I call UART init twice, once for UART 5 and once for UART 6, this single MSP init function gets called twice and they both initialize both of the MSPs. What I like more is to disregard the fact that HAL UART init makes a call to MSP init, and I just don't define this at all. Leave it as the weakly defined symbol, and then I'll just go ahead and call MSP init myself of a different name, so I can actually call those two init functions before calling the UART inits. And that way it's all nicely grouped together, more like a class or object, if you will. Yeah, funny enough, this high-level UART config is object-oriented in that there's a data structure and a method that operates on a data structure, but the MSP init is procedural. Perhaps one better approach would be to say add another field to the UART handle for MSP init function pointer, and that would take a pointer to the MSP init function. That might make more sense. Anyway, I'm going to do what I just said, so I'm going to disregard the MSP init call that is buried inside of UART init, and I will just call my MSP init functions myself. Okay, here's a good starting point. So I'm going to go ahead and copy all this because this looks good and put it into my project. So I'm not trying to organize this well, I'm trying to organize this for the purposes of doing it well later, which basically means I want to keep all of my stuff cohesive so I can transfer it to a new project where everything will be nicer. Okay, I'm doing stuff with this UART handle. Now, what is the UART handle? Declared here. So I'm going to do this, make it static, because if I make it a local variable, it won't be initialized to 0. That got you there. Okay, now I want to define this. Well, first I'll just show that these defined symbols are in this example project main.h. So defining lots of stuff, UART 6. Okay, so back in my project, I'm going to say this is the UART 5. Okay, baud rate, I want to do 115. This all looks standard here. That's good. Don't care about de-initting at first. Don't care about error handling at this point. And then after this, I just want to transmit some bytes. Similar to how after I initialize the LED, just want to exercise it there. So back to the example project. It's doing this DMA transmit, which again I'm not going to use DMA, but just going into the HAL layer here. It is actually laid out pretty nicely. If I just say instead of DMA, I want to do transmit. Actually, I just want to do transmit, so not even with interrupts. Just want to do a blocking transmit here. Handle, buffer, size, and then it wants a timeout. I'll just say 1,000. Now buffer here, I'll just declare one here like this. So now it built here. So this is nice because all I have to do now is get that MSP init to work. So let's look at the MSP init. Yeah, HAL MSP. So I'll just grab that and modify it. Okay, back in my code here, I'll make another function for this. Static. Give it some kind of other name. Can't think of a good name for now. Okay, so don't need any DMA stuff. It's redundant comments here. Don't need DMA stuff. GPIO stuff. RX and TX. Don't need DMA stuff. More DMA stuff. Don't need a DMA interrupt. I'm gonna add interrupts later, but for now I'll just to get this working as fast as possible, just remove those. Okay, so GPIO clocks, USART clock, enable GPIO with alternate function, do that again. Okay, so all these are macros that aren't defined. So here in the main.h of the example project, we have the definitions of all these macros here. So we'll just start grabbing them, just bring them in. Clock, GPIO, pins, okay, DMA, okay, this is all I need. Okay, I'm not actually going to use these defines. I'm just going to remove a layer of indirection here. For example, here when it says USART X, TX, GPIO clock enable, so I want to say UART5 clock enable. Whoops, sorry, that's down here. The GPIO clock is, okay, I have the notes here. Let me scroll up. So UART5, so the TX will be PC12, GPIO C, clock enable, and D. So C and D, UART5 clock enable, don't need that. Okay, TX pin, so this is GPIO pin, so for TX, let's see, pin 12, let's check these helpful auto-completion hints. Okay, alternate function, AF, GPIO, AF, which one's UART5? UART5. Okay, GPIO port, okay, GPIO C, TX for C, okay. Now RX, let's just keep going and do the RX. So RX pin, GPIO pin 2 for RX, alternate function 7 for UART5. Guess it's the same for RX and TX. Okay, RX GPIO port PD, so GPIO D. Let's see if that compiles before we call it. Okay, defined and not used, so let's use it. Okay, I want to call the init before, let's put it here. Too few arguments. We'll just make it void. Okay, it builds. So I can flash now. Okay, notice the scope here is low. Now, again, you can't see it. Take my word for it, the horizontal time base is 10 microseconds. That should show the 100 kilobaud bits nicely. Okay, we just saw the line go up high, so that's good. The idle state of the UART is high, so that tells us that our GPIO has been initialized. I currently have auto trigger, so now I can switch to normal trigger on the falling edge. So that will make it so when bytes actually get transmitted, the scope will trigger and show us nicely there. So now here in OpenOCD, say reset and see if we get the bytes. No bytes. So you see there on the scope, UART transmitter is working. The difference being that I changed the alternate function 7 to an 8. I should have known this. Can't really blame ST for this. Turns out UART 5, depending on the pin and port that you're using, will have a different alternate function number. I guess I just wish that they would have specified that here in the comment. Yeah, both there's a UART 5 in both 7 and 8. I'm using the one, where is it? Yeah, PD2 and PC12. So it's all spelled out here in this datasheet. It's kind of funny that the only thing in this datasheet really is the pinout here. I don't know why they couldn't just put it in the same document as the reference manual. Whatever, just always check. There's always something else you can check if something's not working. Alright, now that the UART transmitter is working, I no longer need the scope here, and I can replace the scope connection with a FTDI connection. So here's a quick tip. You can use these headers as couplers. If you take a hard surface and just press down on the shrouding just a little bit, then that will expose enough pin to connect female jumpers on each side. By the way, here's another tip. Strain relief. Use as much strain relief as possible. The worst thing that can happen is for that micro USB connector to break off. Now in this case it's not the end of the world because it's this connector is a through-hole component, but let me tell you, I had the micro USB connector break off and it was a surface mount component and the pads were ripped off as well, so yeah, try resoldering a surface mount micro USB jack with no pads. I've had success with putting hot glue on the connector, but I don't have any glue right now, so this taping strain relief works. Okay, now my FTDI is connected, so I can verify that the FTDI can receive the bytes. So let's SSH into the remote laptop. Up the screen, let's open up another screen, window, check /dev. We do have a TTY USB 0. Let's verify the baud rate. Set it to 115K, so I do raw minus echo. It's generally okay. Alright, now we can cat. And then here in the OpenOCD window, can reset the target. Oh look, we get hello world. Great. Now I can transmit some bytes on the FTDI and receive them with the STM32. Okay, I want to very quickly do a sanity check that I've configured the UART for receiving correctly. So basically I want to do a blocking receive 1 byte and then transmit the received byte. Okay, let's see how we do the blocking receive. Okay, blocking receive. Alright, let's go back out here. Okay, we got the UART handle, address, okay, receive some buffer, I just want to receive 1 byte here. I'll give it a long timeout so I have time to use the FTDI. Say 10, I believe this is milliseconds, so 10 seconds. Actually, let's make it 100 seconds. Alright, P data, so give ourselves a buffer to receive. Next, buffer 1. RX buffer. Right, did I get that right? Okay. So since that's a blocking call, I can just do another call to transmit here, and I will just transmit the RX buffer, and it's just 1 byte, and see what happens there. Alright, let's do build again. That's good, and now on the host in this project I can flash target remote, and I'm still catting the TTY USB here, so after that loads I should get another hello world, and then over here I'll go ahead and make another screen window. Okay, I got the hello world, so now I can say echo U and send it to dev TTY USB. Alright, I get the U. So I verified that the RX is configured correctly. Now obviously this is not what you would do ever. In a real application you would have some sort of driver layer, or whatever you call it, some code that receives the bytes either in buffers or one by one, and then does some application specific stuff with the bytes. But this video has already gone too long, so I'll just break it up here.